So in this video I'll be working through the velocity and area worksheet that's in the week 1 module, so you can check yourself so you don't wreck yourself. So here is number 1 is just this is if we harken back to the last video where we talked about velocity, total distance being velocity times total time. So again, if we're looking at a velocity curve and this is the time axis and this is the velocity axis, again we know that if we were to turn this into a nice little rectangle, then we know that this distance right here would be t2 minus t1, and this is, of course, right here would be the constant velocity. So that's why we're multiplying constant velocity times t2 minus t1, which would be, this would be my time 2 and my time 1. The time at the beginning of the interval and the time at the end of the interval. Okay, so that's that formula there. We're going to use that idea throughout this page. So number 2 says the graph of the velocity of a rocket is given below. Look at that, it's beautiful. So this, again, this line is telling you how fast the rocket is moving, and the line along here is the time. So 25 seconds after launch, the rocket was moving 1,000 feet per second. That's what this information is telling you. Okay, so part A says use the graph to complete this table of values. So at 10 seconds, the velocity was about 500 feet per second. At 20 seconds, the velocity was about, what, 800. We're just approximating. At 30 seconds, velocity was about 1,200. At 40 seconds, that would be right there, the velocity is at 2,000. At 50 seconds, the velocity is a little above 3,000, so it maybe looks like 3,200. And finally, at 60 seconds, the velocity was right at 5,000 feet per second. Now, find an upper and lower. Now, before we do that, I'm going to go back and draw these little pictures. So at 10, we said we were at 500. At 20, we said we're at 800. At 30, we're at 1,200. So we're making these little blocks, right? You see what I'm doing? At 40, we were at 2,000. At 50, we were at 3,200. And at 60, we were at 5,000. So those rectangles kind of represent what we're showing here. The width of the rectangle is, or the beginning of the rectangle is at 10. Well, you could say the beginning of the first rectangle is at 0, ends at 10. The second rectangle begins at 10 and ends at 20. The next rectangle begins at 20, ends at 30, etc., etc. Okay, so now, for part B, it says find an upper bound and lower bound for the distance the rocket travels between 30 and 40. So between 30 and 40, that would be this distance right here. If we're using these numbers we just came up with, that would be between these two, right? So the upper bound would be, how much time is, or the upper bound, we would pick the fastest velocity, which is 2,000, and we multiply it by my t time 2 minus time 1, which would be 40 minus 30, which would just be 10. So my upper bound would be 2,000 times 10, which would be 20,000 feet per second. Now, my lower bound, on the other hand, I would choose the slower velocity, which is, now I'm going to draw a little line right here. Okay? Let's use a different color just so we don't get confused. I'm going to draw a little line like that. Okay? So my lower bound is going to be 1,200, but also still times 10 because the width is still 10. And that would be 1,000 or 12,000 feet per second. Okay? Now, using 10-second increments, find an upper bound for the total distance the rocket travels between 10 and 60 seconds. So between 10 and 60, so we're not going to use this, so we're forgetting about that part, and we're not looking beyond that. So the total distance traveled. I'm going to make this a little bit smaller so we can see that. Well, as long as I can see that table. So basically what I'm going to say is my upper bound is I'm going to use the upper side of 10 seconds. So the first interval is between 10 and 20. I'm going to use the 800 as my velocity. Okay, so I'm going to say so that means I'm going to go for the upper bound. Did they give me two pictures? Yeah, so this is just the upper bound, right? Okay, so the upper bound, I'm going to go to 20, and I'm going to draw my line there and over. So the first interval is using the, what was it, 800 as my velocity. The second interval is going to use the 1200 as my velocity. The third interval is going to use the 2000 as my velocity. So notice I'm here, here, and here. Fourth interval is going to use 3200 as my velocity, and the last interval is going to use 5000 as my velocity. So now we notice that all of these have a width of 10, so I'm going to put 10 on the outside and multiply it by each one, and then I'm just going to go through and put these velocities in there. So I got 800 plus 1200 plus 2000 plus 3200 plus 5000. So again, what we're saying is that 10 times 800, that'd be 10 times 800. That would be the velocity, that would be the distance traveled during that time period. Then we'd add to that 10 times 1200. That would be the velocity. Let's use a different color, red. That would be the velocity covered in that time interval, etc. And so all I did is factor the 10 out on the outside, so I'm just adding up all the velocities and multiplying each one of them by 10, and that would give me the upper bound. So now if I cruise down here, the lower bound, I'm going to use the left side as my velocity. And that is clearly going to be a lower bound. So once again, the widths are still 10, but this time I'm using the left side. So that'd be 500, 800, 1200, 2000, and 3200. So I'd have a 500 plus 800 plus 2000 plus 3200. And again, the 10 times 500 would be the distance traveled in that interval. The 10 times 800, why did I cross my 1? 10 times 800 would be distance traveled in that interval. And then the 2000 there. Oh wait, am I missing one? 1, 2, 3, 4, 5, 1, 2. Oh, I missed one, didn't I? Shoot. Glad I looked that back over. That should have been 10 times 800, times 500 plus 800 plus 1200 plus 2000 plus 3200. Okay, so the first pair goes there, the second pair goes there, and you can see that's the third interval, the fourth interval, and the fifth interval. Okay? So now it says, give an illustration of the difference between the two bounds found in parts C and D. Write a formula for the relationship between the two bounds, the velocity function, and the time interval. So what that means is that you can tell on that first interval from 10 to 20, remember I use the lower bound was right here, and the upper bound was right there. So this little rectangle represents the margin of error, so to speak. And we could do the same thing for the next one. The lower bound is right there, upper bound is right there. So that represents the error. lower bound, upper bound, there's the error, lower bound, upper bound, there's the error, and finally lower bound, upper bound. So those little rectangles would represent the difference between the upper and lower bounds, or the margin of error. We know that you can see that the rectangle is kind of straddling, each one of the rectangles is straddling the velocity curve. Okay, so then this part F says how often would measurements of velocity need to be taken so that the difference between the upper and lower bounds is 1,200 feet. So you can see I'm not so worried about you doing this. This will take a little bit of time, but basically what you're going to try to do is try to get this total area less than 1,200 feet by making your intervals smaller. So what happens when you make intervals smaller? You know, what will happen to the areas? Well, I should have left those actually. Let's leave those. And we'll use red to do this. If I make them smaller, notice then we just got one like this. Excuse me. Then the interval is there and there, there and there, there and there, there and there. You can see by making smaller intervals, that makes my error margin smaller. There's less wasted space, so to speak. And that's, again, illustrating why when we make smaller intervals, the area, the smaller the intervals, the more accurate the approximation. So basically what we're doing is trying to make, if we just keep getting it smaller and smaller, those little rectangles get smaller and smaller, and we're trying to get that total area of those rectangles to be under 1,200 feet. Okay, so sigma notation, this is kind of where we're headed. So the idea here is, if I'm trying to get the margin of error really small, what I'm really trying to do is trying to get the area under the curve approximation really accurate. And when we start getting a lot of rectangles, it gets really confusing, because right up here we just had 5 rectangles, and I lost track of one of them. So what we do when we're adding up a bunch of little things is we use sigma notation. And you've seen sigma notation before, but you may not be that familiar with it. Sigma notation looks like, oh, let me use a black color. Sigma notation is basically, you use this giant sigma, which is a Greek letter, and there's usually some kind of indice like an I, and we let I start at 1 or 0, and we let it run to a certain number, and that number goes up here. So in this case, we're going to let it equal, say, 100. So that means I'm going to break this, the number of rectangles that I'm using into 100. So instead of doing like up here, we're going to erase this real quick. Instead of doing every 10 or every 20 or every 10 or even 0, we're going to do every 100. So that means we're going to have a bunch of these teeny little rectangles being added up. Hundreds of them, actually 100 of them. And so what we're trying to get at is, what would the area of all those rectangles added up look like? Well, if we look at the first one, let's take, if we're going from 10 to 60, I'm sorry, I started that too early, didn't I? Should go right there. So there's the first one. We'll just pretend it's smaller than that, obviously. But first question is, how wide is that rectangle? And I would advise that you pause the video for a moment and think about that before you let me answer it. So I'm assuming that you've paused and you're back in now. So the width of that rectangle is just going to be the total time interval from 10 to 60, which would be 50, divided by the number of rectangles, which we said was 100, so that would be 50 over 100. Okay, so that's the width of each rectangle. Oh, I didn't know I could do that many different colors. It's pretty cool. How did I get those different colors? Okay, so width of each rectangle. So that means that this little width right here is just going to be 1/2 of a second, right? Because this 50 over 100 reduces to 1 over 1/2, or 1 over 2. So if I want to find the area of one of these rectangles, so like that one for example, that would be the area, the width would be 1/2, and the height in this case, now I'm going to do a right-hand sum, so that means I want to know how big that one there is. So that would be the velocity evaluated at, and I would plug in 10.5. Because I'm looking 0.5 over from 10, and I want to plug in 10.5 to get that value right here, because that value is the velocity evaluated somewhere for some x, right? So basically what this expression is going to look like is for the upper bound, because we're using right-hand sums to be upper bound, the sigma notation for the upper bound is going to be 1/2 times velocity evaluated somewhere in time. So the way sigma notation works is you just come up with an expression for finding each one of the areas, and then what this little I does is run you through each one of the areas. So this would be like the velocity of the first time interval, then the velocity at the second one, and then the third one, etc. So this is going to look like 1/2 times velocity at t sub 1 plus 1/2 times, 1/2 times velocity at t sub 2 plus 1/2, get out of the way guys, one-half times velocity at t sub 3. So all these little time intervals. So in this case, this would be 1/2 times velocity of 10.5 plus 1/2 velocity at 11 plus 1/2 velocity at 11.5, because you can see each interval I'm going over 0.5 plus ... all the way up to 100. So the next video I'm going to be talking about how to get into the particulars of this, but this is the idea, is that you want to I'll have to explain more about sigma notation, but the idea is I can write expressions for the areas of these curves broken up into hundreds of rectangles rather than just a couple. Because if we can do just 5 like we did here, we can actually just calculate it, with our on paper and stuff. But if we're going to do more than 5 or 6 rectangles, like hundreds or thousands, then we really need some other way to express it, and that's where sigma notation comes in. All right.